Hi, welcome to the screencast for the extra practice for topic 10.4 to 10.6. Number 1 asks, what's the final product formed when 1-octanol is refluxed with acidified potassium dichromate? Structural formula, name the product, and the color change. So final product is your hint that it's going to undergo oxidation twice, and octanol once, letting you know it's a primary alcohol, so that's possible. So it's going to go from octanol to octanoic acid. It's going to become a carboxylic acid. And so that means I'm going to have CH3, and this is a straight chain because there's no branches indicated in the formula. So CH3 with 6 CH2 groups, and then COOH is going to be my final group. And then the color change is going to be, you're going to oxidize orange. You're good to go when it's green. So orange to green would be the change. Number 2 is similar. It says propene can be converted to propanoic acid in 3 steps. So propene, remember, has got that double bonded carbon in it. So you're going to add an H2O to it to get the, I guess I could just write the name here. So it's going to become propanoic acid. Or propanol, I'm sorry. Ahead of myself here. And then after propanol, it becomes an aldehyde, so it's just a matter of changing the letter there. I can't remember if propanol has an A after that second P or an O, but you get the idea. So it's OL to AL, and then propanoic acid. Identify the type of reaction occurring to form. The first one is hydrogenation. Remember, that's slightly different than hydration, because it's hydration, not hydrogenation. Wow, I should do this early in the morning. So it's hydration. Okay, so here's what we're starting with here. We've got 3 carbons to form our basic propane, and then the 2-iodo-2-methyl means there's a CH3 group and an iodine, both coming off that middle carbon. And then the KOH, what's important here is the OH group coming in, and it's an SN1 because this iodine has to break off. And so the first thing you're going to show is that it's taking the electrons and breaking off. And at this point, the OH can't get in there with an SN1 mechanism, because remember, this is a secondary halogenoalkane, so it could undergo the SN1 or the SN2. And since they indicate SN1, it means that the iodine is going to break off first. So in my second step here, I'm going to see the CH3, CH3, 2, and that's now going to have picked up a positive charge because the Cl has left, and now I can show that the OH is inserting its electrons in, and then I can show my final product is going to be the CH3, CH3, CH3 with the OH here. Number 4 then says, which formula represents a tertiary alcohol? Without having to draw these, this is actually fairly easy to figure out, because as you look through, tertiary means there have to be 3 ends. So you're looking for 3 CH3 groups. So there's CH3, there's CH3, there's CH3. This one only contains 2 methyl groups, 2 methyl groups. And then this one also has 3 methyl groups. So now I'm going to have to sketch them out to see which one actually, or think a little more anyway, about which one actually has 3 carbons attached to the same carbon that has the OH on it. So if you take a look at this one, you can see that this middle carbon is going to have a CH3 group here, a CH3 group here, and then the OH group attached, as well as the next CH2 group. So that one is a tertiary. This one, though, this CH group, it's only a secondary because there's an OH hanging off and then a CH3 and a C this way. So A would be my only one that fits the definition of a tertiary alcohol. Number 4, drawing the structure for 4 isomers of butane, of bromine, halogenoalkane. So I could have 4 in a row, and the Br could be here. I could have 4 in a row, and the Br could be off one of the second carbons. I could have 3 in a row, and the Br could be off here. Or I could have 3 in a row, and the Br could be off the center one. So then naming these, if I could squeeze this in, this would be 1-bromo-butane because it's straight chained. And then this one would just be 2-bromo-butane. These other two then are going to be 2-methyl-propane. And then the question is, where does the bromo comes in? So this is the 2-bromo comes first, since we do it alphabetically. And then over here, now let me think about that. That name goes down here. This is the 2-bromo, 2-methyl, propane. And up here, this name I've got to erase and amend slightly, so let me pause a second. Okay, so for our last one here, I'm sorry I couldn't erase that, but instead what I'm looking at is, this is now my longest chain, so I would call this 1-bromo, 2-methyl, propane. Moving on then to number 6, or I guess we got more of number 5 here. Let me see if I can erase that while I'm here. So explain what is meant by the term nucleophilic substitution. And really all they're looking for is that an atom of a compound is replaced by a species with a lone pair of electrons, or a nucleophile substitutes for an atom on some compound. The number 6 says, draw the structure for the straight chain primary isomer C4H9. So this is our simplest one, and I'm just going to draw it with the bromine. I'm not going to fill in the hydrogen since they're really not pertinent to it. Show the SN2 mechanistic equation for this isomer, so I'm going to add OH to it. And so then using the arrows, you should show that bromine is taking the pair of electrons as oxygen tries to bring them in. The arrows come and go from the bond itself, not from either atom, because you're trying to show transfer of the electrons. And then this will form the intermediate product, where you end up with both the bromine and the OH attached. So now you've got a negative charge there, and then your final product would be the alcohol group and the bromine ion. And then draw the structure for a tertiary isomer and show the SN mechanism for this. So we've seen this already on this worksheet, but practice makes perfect. So now the OH group is here, and so, well, not the OH group, the Br group is here. And so with the tertiary mechanism, the Br has to break off, and we have to have a positive here, and the OH now can move in, and then we have a final product with the OH. Okay, then number 6, look at the following alcohols to decide if oxidation would take place or not. Names are much easier to decide because the name tells you. So 1-butanol, it's primary. So yes, it could form 2 products. It could form an aldehyde, and you could just go ahead and name the aldehyde. And it would also form a carboxylic acid, or again, you could just go ahead and name the acid butanoic acid. And then 2-butanol is a secondary alcohol, and it would also undergo oxidation to form a ketone or butanon. And then 2-methylpropanol, that's a little harder to tell, but it's a tertiary if you think about the structure or draw the structure, because you've got the OH group off, and then you've got 3 carbons attached to that. So this would have no oxidation. Number 3.1, so which compound is a tertiary halogenoalkane? So we're looking for the bromine to be attached to a carbon that also is attached to 3 other carbons. So if we look here, here the bromine has a carbon with a hydrogen on it, so that can't be it. Carbon with 2 hydrogen, no. Carbon with 2 hydrogen, no. And this is our winner here, because you have a carbon attached to 3 carbon groups as well as the bromine. So that would be your tertiary halogenoalkane. Number 7, which species reacts most readily with propane? So propane, if you think about it, is an alcohol, a CHO group on the end there. And so, I'm sorry, not an alcohol. Propane is just an alkane. And then the alkanes are the ones that undergo that endothermic, very unusual reaction where the initiation, propagation, and termination. So B, that's representing a free radical. And it really doesn't matter if you put the electron, that unpaired electron, on the left or the right. I mean, I suppose actually you could put it on the top or the bottom. The idea is it's an unpaired electron that you're indicating by that. Number 9 says CH3CO, CH3 can be prepared from an alcohol. State the name of the alcohol. So this is a ketone because the oxygen's in the middle. So the name of the alcohol this came from would have been propanol. The type of reaction occurring is an oxidation. And then the conditions and reagents needed is that you need heat, and then you need your acidified potassium dichromate, and it's dichromate 6. And then, of course, you'd need oxygen as well if it's going to be an oxidation. And then that's a ketone. So reflux or not reflux, either one is fine for that one. Number 10, 2-bromobutane can be converted into butanol 2 by nucleophilic substitution. Give the structure of the transition state. So SN2 means there's going to be 2 things attached to it. So 2-bromobutane, I'm just going to draw this down here since I have the room. Butane is going to be CH3. And then my C group is where I'm going to have the bromine hanging off. So I've got 1, 2, 3, and then there's my 4th one. So CH2, CH3. So there's my structural formula. And then if it wants the SN2 transition state, that means I'm also going to have an OH on here at the same time, giving it a total of 5 and giving it a negative charge. And remember, this is a secondary halogenoalkane, so either an SN2 or an SN1 is possible. And part B then is asking for the complete equation for the SN1. So the SN1 would start out the same with the bromine, and to show the complete equation, you'd show that the electrons are being transferred. Oops, arrow here. And then you've got 2 transition states because you'd have the SH3, CH, CH2, CH3, and you have a positive charge associated with this. You could just put it at the end. I'm putting it near the carbon where it's occurring. And then your final product, and I guess at this point also you would be showing that the OH is donating its electrons, its electron pair. And then my final product would be CH3, CHOH, CH2, CH3.